To recap, if I let x, apologies for the crazy dogs downstairs, if we let x be an alphabet of n letters, um, the number of words of length k with the alphabet x, remember, if we have no other restrictions, the answer here is n to the k. Number of permutations of length k, which is a word of length k where you don't have repeated symbols, is pnk, which we learned is equal to n factorial over n minus k factorial. And the number of subsets of x of size k, which is just a collection of k of the symbols where we don't care about the order or anything like that, is n choose k, which we also have this alternative notation cnk, and that's n factorial over n minus k factorial. Sorry, the writing's not great there, but yeah. So today what we're going to do is focus more on this last type of number, this n choose k thing, and look at some, in particular, we're going to look at some cool applications which are not completely obvious of the number n choose k. So here's the first question to think about. Suppose you have 8 identical cookies, okay? 8 cookies, and you have 3 hungry children. How many ways can you give the cookies to the children so that each child gets at least 1 cookie? And this is not supposed to be obvious because, it takes a little bit of thinking. So what you might do if you want to work out the answer is you might just try to go through all the possibilities, right? So here are some of the possibilities, right? The first child could get 1 cookie, the second child gets 1, the third gets 6. That's an option. That's obviously not very fair, but oh well. It meets the restriction. Or the first child could get 1, the next one could get 2, third one could get 5, and all of these are different options, right? 1, 3, 4, 1, 4, 3, 1, 5, 2, 1, 6, 1. And note that here, because the children are all different, right? So in particular, this option is different from this one, right? Even though they're both like kind of 1, 1, 6 in some order, we consider these as being different, if that makes sense. Ooh, yeah. Okay, because different children get different amounts, but even though it's still 1, 1, 6 in some order. But obviously, if you just went through this, this is going to be terrible, right? And especially if the numbers get bigger, we have 30 children and 500 biscuits. This is not going to work, right? You can't just go through all the possibilities. So there's got to be a better way. So let me now show you the better way. So these are our cookies. They're supposed to be identical. I should have just copied the same picture over and over, but for some reason I drew them all. They don't look identical, but let's say from the perspective of the children, these are identical. Yes, so we do have an answer coming in the chat, which appears to be the right answer. But let me just explain why. So we've got 8 cookies. They're identical. It doesn't matter who gets which cookie. It just matters how many cookies they get. So a way to think of dividing this between 3 children is to think of the gaps between the cookies. Like imagine you write them, you put the cookies in a row like this, and you look at these gaps. And what we want to do is we want to put a dividing line in the gaps. So we want to put 2 dividing lines so that it breaks the cookies into 3 groups. And once you put the dividing lines, that completely determines how many each child gets, because we'll just give the left group of cookies to the first child, the middle one to the second child, and the right one for the third. So we just throw in some dividing lines, maybe there and there. And no matter how you divide it, if you choose 2 different gaps, so you don't put 2 lines in the same gap, you choose 2 different gaps, then you can always just give the first group of cookies to child 1 and 2, 3. So therefore the number of choices is going to be the number of gaps, which since we have 8 cookies, there's 7 gaps between them. And then we choose 2 dividing line. So it's 7 choose. And note that this will have the right properties, because if 7 choose 2 will choose 2 different gaps. It'll never choose the same one twice. That's the type of thing that 7 choose 2 counts. And now if you think of it the other way, if you have a way of giving cookies, you can also think of it in terms of these gaps, right? If you gave some number of cookies for the first child, you just count that many cookies to the left, put a gap there, or put a divider there, and so on. Is this clear? Okay. If I don't have any questions, then I'll assume it is. Okay, here's a variation. Oh yeah, actually maybe I'll put this to another poll. Let's try to be quick with these polls, and then yeah. Oh no. I don't want this poll. How do I do another poll? Oh, here we go. So what if we, instead of having 8 cookies, 3 children, what if we had n cookies and k children? Okay, so maybe I'll stop the poll in 5, 4, 3, 2, 1. Okay, so I don't know whether I should be sharing these results or not, but yeah, so most people got the right answer or some variation of it. So the right answer is indeed n minus 1, choose k minus 1. Why? Because if you think of it, if you have n cookies, you have n minus 1 gaps, okay? And you're going to choose k minus 1 to put a divider into. And when you put k minus 1 gaps, k minus 1 dividers, that breaks the cookies into k groups, right? If I put 1 divider, that breaks into 2 groups, 2 of them put it into 3 groups, and so on. Okay, so so when you encounter these problems, this is going to be, so n minus 1 choose k minus 1 is often going to be the answer. Okay, now a variation of this problem. So remember I told you that every child has to get at least one cookie, which is, that seems like a nice thing to do. I mean, honestly, you should probably give the children the same number of cookies. But yeah, it seems very mean to not give one of the children any cookies. But let's say we go with that. So we have 8 cookies. We're going to divide them into 3 groups, and we have no restriction. So some child could get 0. So now it's still kind of similar to dividing lines, right? Because, except the only difference is that the divider can be in the same position. That makes it a little bit trickier to think about, actually. So I should point out, so in this, the way I want to phrase this one is that all of the cookies will go to some child. So it's not the case, we're not allowing the case where I keep 8 of the cookies and eat them myself. Every cookie goes to a child in this example. But we could also consider that example as well. But yeah, good question. So every cookie gets distributed, and it's possible for a child to get 0. So if I put the divider, I put the dividers in the middle here, for example, that would mean that the first child gets 4, the second gets 0, the third gets 4, for example, right? There's 4, 1, 2. Okay, here's a nice way to think about this. So we do have an answer coming in the chat, which does appear to be correct. Let me tell you why it's correct. So the answer is going to be 10, choose 2. Here's how to think about it. We're gonna introduce a few imaginary cookies. So take the 8 cookies and add an extra 3 cookies. And these cookies don't have to really exist. They could just be, this is just for the kind of thought process of solving the problem. So we add 3 imaginary cookies to our set of cookies. And now what we're going to do is divide the cookies among including the imaginary ones, among the children, so that each gets at least 1 cookie. Okay? And we know how to do that. We just solved that problem, right? So I guess in the previous slide I was using 8 and 3. If you have n cookies and m children, this would be n, the number of cookies. So this is n, and you'd add an extra 3, which is the number of children. Or sorry, another k, let's say. K is the number of children. Okay, so we take these n plus k cookies, or in our case, in our example, it'd be 11 cookies, and we're going to divide up those 11 cookies. And then, so that every child gets at least 1, and then we're going to take 1 away from each child, right? And then since every child got at least 1 before, now every child gets at least 0, if that makes sense. Okay, and we still have and then we have exactly n cookies because we introduced k extra cookies, we distributed, then we took away k cookies, 1 for each child. So how many ways are there to do this? Well, it's a number of ways to divide up n plus k cookies among k children, where each child gets at least 1. And we already kind of determined, we solved that problem before, with the number n taking the place of n plus k. So it's n plus k minus 1, choose k minus. Okay, you can think of it once again as putting k minus 1 dividers between your cookies. Is that clear? Okay. So let's now look at another question. So kind of change gears. How many integer solutions? So meaning, when I say an integer solution, I mean a solution to the inequality or to the equation. So the n plus k minus 1 comes from the fact that, so we took n cookies, we increased the size to n plus k, okay? So we have n, here, imagine there's n plus k cookies. Even, you don't have to go bake more cookies, but you just imagine there's n plus k. And how many ways can I divide those up into k bins? Well, that's the same way as choosing k minus 1 dividers. But here I'm dividing them into k bins so that all the bins have at least one cookie. So that's the number of ways to choose k minus 1 dividers. And once I do that, I then take away a cookie from each child. And that's the same as just giving the cookies to the children in such a way that they can have 0. Okay, yeah. So the k extra cookies, this is just a thought experiment to solve the problem. You don't have to go bake them. So here's the thing, the cookies are all identical. So there's a question about why it's not n plus 1 to the k minus 1. The thing is, yeah, the cookies, they're all identical. So it doesn't matter which child gets which cookie, for example, if that makes sense. Yeah, or also, yeah, we're choosing, also it doesn't matter that where the first divider line, like you're not, the divider lines are not kind of ordered in some way. So we're just choosing a subset of the gaps to put a divider lines. It doesn't matter, like we don't say I put the first divider line here, second one there, third one there. It's, yeah. Oh, maybe the question really is about, yeah, I'm not sure, but okay. I should move on to the next topic. Yeah, that's basically what I'm trying to say. Yeah. Yeah. The order of where you put the dividers doesn't count. So yeah, that's right. Yeah. So if you do want to just remember these formulas, you can. Personally, for me, I find it more useful to also remember the justification, because then if you forget the formula, you can always just work it out for yourself. But yeah, if you do want to just remember the formula, that also works. Okay. But the difficulty with just remembering the formula, obviously, is that when the questions get harder, you may not see when to use what formula. So that's one reason. Okay, so how many integer solutions are there to x1 plus x2 plus x3 plus x4 equals, let's say, 92 for a random number, such that all the xi are at least 1. And integer solution, I mean that, that each, so how many ways can I pick all the xi's? So each xi is an integer. And we have this restriction that all of them have to be at least 1. So you can't use, if you could use negative numbers, the answer would be infinity, right? I can just let x1 be, very negative and then whatever. But each xi is at least 1. And the hint here is to think about cookies, right? Think about xi as being the number of cookies that child 1 gets. So, or xi is number that child I gets, number of cookies. Yeah, exactly, 92 cookies. So like, and this is, yeah, because, so it is important, by the way, that the cookies are all identical, or else this wouldn't be the same. But given that the cookies are all identical, you can imagine we're trying to give 92 units of something to x1, x2, x3, x4. Yeah, it's going to be a long night. Yeah, 92 cookies is quite a lot. Yeah. Okay, so this is really the same problem, but this is just written in a sort of more mathematical way. But basically, if you can turn your problem into this one or into something about cookies, then you can always kind of solve them. So here the answer is going to be then 92 minus 1, choose 4 minus 1. So in other words, 91, choose 3. And again, if you want to think back to the principles of this, you could imagine you write out, say, 1 plus 1 plus 1 dot, equals 92. Or why did I write 32? 92. And you can think of dividing these ones into 4 bins by breaking at the plus signs, 3 plus signs. Okay, so this is really the same question. Here's a variation. So what if we have slightly different restrictions? So we say that instead of all of them being at least 1, we say that x1 has to be at least 1, x2 has to be at least 1, but x3, x4, x5 are a bit different. So that one has to be at least -2. Or sorry, x5 is fine, it's at least 1. x4 is at least 7. Here, this is kind of like when we took the children and we said instead of getting at least 1 cookie, they have to get at least 0. So what we're going to do is actually kind of modify the number of cookies in a sense. But that can be thought of in terms of changing variables. So let's say I let y3 be x3 plus 3, and I let y4 be x4 minus 6. Okay, so all I'm doing is kind of changing variables here. And then if x3 is at least -2, that's the same thing as saying that y3 is at least 1. And if x4 is at least 7, that's the same thing as saying y4 is at least 1. And let's say we also define some other things. So let's say we let y1 be x1, y2 be x2, just for completeness. Y5 equals x5. Okay, so now our condition about the x's turns into a condition about the y's, and it's a much simpler condition because it just says, all of these conditions become just saying that yi is at least 1 for all I by how we defined these things. Here's one thing you shouldn't forget. So what you could now consider doing is just solving this problem with the yi's, but actually this is going to be the wrong number now. So here's the thing. If suppose that x1 plus x2 plus x3 x4, well, maybe I'll avoid writing something I've already written here. So if x1 up to x5 adds up to 78, then what does the y's add up to? That's what you should be thinking now. So this is the same as saying that y1, y2, y3, y4, y5 adds up to, oh dear, I have to do math. 78 minus 6 plus 3, which is 75. So what we do then is we solve the problem with the y's. So y1 up to y5 equals 75, with the constraint that all of them are at least 1, and the number of solutions, as we've already seen, is 75 minus 1, choose 5 minus 1. So 74, choose 4. Okay, so this is what you should do when you see problems like this. You should think about doing a change of variables. And this is actually the same thing we did with the children and the cookies when they could have 0 cookies. It's sort of like we did a change of variables where we added 1 to each child and then we solved the problem in some sense. It's kind of like defining yi to be xi plus 1 and then solving it. Are there any questions about this? Yeah, many different variations. Yeah, so this is kind of more like the children thing. So, there's a sneaky thing here. So this is the only thing I haven't told you how to deal with. What if I have integer solutions to this equation where instead of an equal sign, we have a less than or equal sign? I claim that this can actually be done in the same way, essentially. Yep, so someone in the chat has given the right suggestion. That's exactly what I want to do. So what I'm going to do is introduce a new variable. Let's call it x5. And we put the constraint that x5 is always non-negative. And then we count the solutions to x1 plus ... Well, okay, I won't worry. ... x1 plus x2, x3, x4, x5 equals 90, what is it, 94? Where all of the xi are at least 0. And then if you wanted to turn this into xi at least 1, you could then change the variables to y1 up to y5 or something, and change this constraint to something else, to, I guess it'll be equal to 99, right? So if all of these x1 up to x5 equals 94, then if I take away the x5, then x1 up to x4 will be at most 94. So the answer now is, well, it's going to be 99 minus 1, choose 5 minus 1. So 98, choose 4. The 99 comes because we have these this type of constraint that's at least 0, not at least 1. So this is sort of what I'm trying to say about like memorizing formulas versus understanding the reason. It's actually quite helpful to to remember the reason for these things rather than understanding the formula, because you can see that with a few steps of extra stuff added, this can become quite complicated. So understanding this thing about dividing lines and stuff really can help. Okay, so this is how you would solve this one. Any questions about that? Okay, but yeah, that being said, you should solve the problems however is best for you. Okay, Here's a slightly trickier one. So we've got x1, x2, x3 add up to 71. X1 and x2 have the usual constraints. Nothing interesting. They're at least 1. So they're at least 1. And now I've got x3, which is at least 1 and at most 42. So any thoughts on how I might deal with this? So there are, I mean, in theory, there's different ways you could think about it, perhaps. For example, you could think of every different value for x3. You could solve those individually and add them all up. I don't think you should do that for your own sanity. Or you could write that as a sum, which is a little bit better. Or there's a nice way to do it by counting the complement. So what I would suggest here is first, so step 1, count the solutions where you have just xi at least 1 and no restriction that x3 is at most 42. So you first ignore that restriction, right? And that'll give you an answer. And the answer, I guess, will be, does anyone know what the answer will be for this? So I'm going to go with 70, choose 2, right? Because again, it's like choosing 2 dividing lines between 71 cookies. There's 70 different gaps. And now what we're going to do is subtract the solutions that we don't want. So we counted every way of doing this, even where x3 goes too large. Now we have to just subtract the ones we didn't want to count. So count the solutions with x1 at least 1, x2 at least 2, or sorry, at least 1, x3 at least 43. Okay. And then, and I guess the answer to this one, so it's going to be, well, 71 minus 41 is 30. I think this is going to be 29, choose 2. Okay. But you can think about that yourself in terms of changing variables. I might have got this wrong, so please do correct me if I'm wrong. I just did that quickly, but that's just changing variables like we've done before. And then, I've definitely done that wrong. Let me fix that. So that should be, I think, 28. Yeah. 28, because I subtracted 41. I should have subtracted 42 because of, that's 43, not 42. Right. So, and then subtract them, right? So this is again, this nice trick. I love this trick, counting the complement. Count a whole bunch of stuff, including everything you want, but with some extra stuff you didn't want. Then count the stuff you didn't want and subtract it. So final answer, 70, choose 2 minus 28, choose 2. And on an assignment or a test, you can feel free to just write that as the answer. You don't have to compute the values. On a quiz, you might be asked to compute the values, but not on a test. Okay. Oh, I guess I planned to do that here, but I've already done that on the previous slide. Okay. Here's another cute application of binomial coefficients. So I want to count different ways of walking through a grid, essentially, from one point to another. So here's the setup. So I start at the origin, and the rule is, at each step, what you're allowed to do is move either 1 unit up or 1 unit to the right. So when I say up, I mean, of course, like in the positive y direction, and here I mean in the positive x direction. And here, when I say or, I mean you're not allowed to do both. So like exclusive or. So you're allowed to take a step up, you can take a step right. And now what I'm wondering is, how many ways can you walk from the origin to the point n, m? So this picture shows some examples of some paths, right? So you can either, if I'm walking from 0, 0 to 7, 4, I can walk up, right, up. So this is the green path. Green path goes up, right, up, right, up, right, 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 right. So that's an option. And then I've got all these other paths. Okay, we want to count all the paths. Okay, well, so what do we think? So there's a question in the chat now about whether you're allowed to exceed the height of the destination. So I'm not going to specifically say that you can't, but the rules of the game sort of dictate that you can't, because since you're only allowed to go up or right, once you go past the destination, once you go above it, there's no way to get down, right? Because we don't allow a negative y step. So the answer is that no, you can't exceed the height because you would never be able to get back. That's a good question, though. So we call this kind of path a lattice path. So if I ever say those words, this is what I mean. It's one of these right or up paths. So how many total steps? So yeah, we do have an answer in the chat, which turns out to be the right one. But let's derive why that's the right answer. So how many total steps do you take if you're going from 0, 0 to nm? And if you think about it, you have to take n steps that go right? So there's n to the right plus m that go up. And because of this fact that you can't exceed the height, because you'll never be able to get back down, the total number of steps you're going to take is exactly n plus m. It can't be less, it can't be more. If it's less, then you can't get to the right height or the right far enough to the positive x direction. And if it's more, if you take more than n plus m steps, there's also a problem there, right? You're not going to be able to do it. You can't, because you can't go back and stuff. Oh yeah, so here, n go to the right, m go up. And basically now all we get to choose is which steps go up and which steps go right. We know we're going to take n plus m of them. We just need to know which ones are up, which ones are right. So how many ways can I choose that? Well, choosing which goes up and which goes right is just the same as choosing which ones go up, right? Because if I choose which ones go up, the rest of them go to the right. So we have n plus m steps, and I can choose n of them to go right. And note that this is not, so it might look fishy, right? Because by the same argument, the same thing gives me n plus m, choose m. If those were different numbers, then this would be bad, right? Because I can't have two different answers to the same question. But they're actually equal, because we know this basic fact from last time, that n choose k equals, or let's use different letters. Let's avoid n right now. Let's say r choose k, or let's say t choose k equals t choose t minus k for all t and k. Right, so if you apply that rule with t equals n plus m, you'll see that these are the same, so there's no obvious contradiction in what I'm saying, okay? So the point is you take n plus m steps, and you just have to choose which of them go up or right. Any questions about this? So whenever I talk about a lattice path, this is what I mean. Okay. Oh, yeah, so just for the sake of kind of completeness, and a lattice path doesn't have to start at the origin. So the only rule about a lattice path is it has to go up or right in every step, but it can start anywhere. So let's suppose I start at 2, 4, and I go to 10, 17. So I'm not starting at the origin, I'm starting somewhere else. So the answer is going to be, because, I mean, basically starting at 2, 4 isn't that different from starting at the origin, right? But I just have to keep track of how many steps I need to do and stuff. So you can think of this as going from the origin to 10, 17 minus 2, 4, which is 8, 13, 8 comma 13, right? Because that's the same thing. If I start at the origin, I go to 10, 17, that means I have to take 8 steps up and 13 to the right, and that's the same thing. So by the thing we derived in the previous slide, this is going to be 21, which is 8 plus 13, choose 8. Or choose 13, it doesn't matter because those are equal. So let's do a poll. If I can figure out how to... okay. How many ways? From 3, 1 to 9, 14. I better figure out the right answer. So, and do feel free to put, if you don't know the answer, feel free to pick I don't know, because this is anonymous, so nobody gets to know who picked what. Okay. I think I'll still release the answers if that's fine, release what everyone chose, but no one will know who chose what. Okay, let me share the results. So yeah, this is kind of math by democracy, right? Whoever, okay, it's not, because if you do vote, if the majority did vote for the wrong thing, I would tell you that, I guess. But yeah, so the people are right on this one. So it's 19 choose 6. Reason is right. So basically, it's the same as going from 0, 0 to 6, 13. 6 plus 13 is 19. So it's going to be 19 choose 6 or 19 choose 13. I didn't give that option, but if I gave you the option 19, choose 13, that would be correct as well. I should have given both and just see, whether one's more popular. But okay. Any questions? Okay. Please give me feedback about this. Like, I don't know if this polling thing is any good or not, but I think it's good for you to think actively about this rather than just kind of waiting for me to give you the answers. That's at least my theory, but if it doesn't work, it doesn't work, right? Okay, so for the last 25 or so minutes, let's talk about another topic, which is kind of a smaller topic. It's something called the Pigeonhole Principle. So it's I'll tell you that on the surface, this is going to sound like the most trivial thing ever. But like all of these things that we're doing, the difficult thing is kind of recognizing when you need to apply it and being able to kind of set the problem up so that you can apply the principle. But the basic principle is not, I hope it's not too difficult to understand. It's just that, so if let's say I have n plus 1 pigeons for some number n, and let's say those pigeons fly, so they're all going to go into a hole. So every pigeon goes into some hole, but there's only n holes. So then the only conclusion I've got here is that there must be a hole with at least 2 pigeons. I've forgotten how to spell pigeon. Is this how you spell pigeon? There's no D in there, I think. Pigeon, pigeon. And here's an illustration. We've got 4 pigeons. We have 3 holes. Imagine they're all trying to get into the holes. Well, there has to be a hole that has 2 pigeons in it, kind of proof. Okay. It's not a proof, but it's, yeah. I don't think that, so this is probably a statement that doesn't really need a proof. Yeah. Any questions about this? Okay. Right. So imagine, so here's an example of how to apply this. So imagine I take 27 words from the English language. Okay. Remember, so, I don't want to make somebody's ability to solve problems dependent on how familiar they are with the English language. But I'll just repeat that so English has 26 letters in total. So suppose you take 27 words from English, then there must be 2 words starting with the same letter, right? And the way to think about this in terms of pigeons is, imagine you have 1 hole for each letter. So you have a hole for each letter. My pigeonholes kind of look like my cookies, except a different color. So you have 1 hole for each letter, A, B, C, D, E, F, and so on, down to Z. And let's think of the words, the words as being pigeons. So each pigeon flies into the hole, which is corresponding to its starting letter. And there must be a hole that has 2 pigeons in it by the pigeonhole principle, because there's 26 holes and 27 pigeons. Any questions about that? So these questions might not, so here I've kind of, the number 27 here maybe is making the question easier than it might be otherwise, in the sense that, I don't know, 27 is exactly 26 plus 1. But these questions might be presented in different ways, right? So I can say, in any set of 375 people, there must be 2 people with the same birthday, right? And that's just because 75. I don't know whether we should count leap year, like February 29th. Let's count February 29th as a legit birthday. So there's 366 possible birthdays. 375 is bigger than that. So basically there's more pigeons than there are holes. So there must be a hole that has at least 2 pigeons, if that makes sense. Any questions about that? So these are holes, which are birthdays. Yeah. Oh, okay. Yeah, I wasn't aware of that. Thanks. I will, in the future, I'll try to keep the stuff away from the bottom then. Thanks. How far down can you see? Can you see there must be 2 people with the same birthday thing? Okay, so then it's just this stuff, which I don't really have anywhere better to move it. I'll put it, well, maybe, anyway. But the point is, yeah, there's only 3, if you count leap years and stuff, there's only 366 possible birthdays. There's 475 people, which is bigger, and they, yeah. Okay, so it seems possibly, depending on where you're viewing this from, in terms of how your computer does zoom, or maybe your dimensions of your screen or something, maybe you won't be able to see the bottom. I'll try to keep things away from the bottom going forward. Okay, so this is now kind of an inverse problem in some sense. Like I tell you, I give you a number n, or I say, well, I don't give you a number n. So I say, suppose you are going to write down n. So it is kind of computer dependent, possibly, or smartphone or tablet or whatever you're viewing it on. It could be covered by some taskbars and stuff like that. Okay. So suppose you write down n binary strings of length 6. Do we remember what a binary string is? Right? It's a string with alphabet 0, 1. You write down n of them of size 6. How big does n have to be to guarantee that 2 of the strings are the same string? So, well, if you think of each string as being a whole, or each possible string as being a whole, and you think of each string that you write down as being a pigeon, you just need one more pigeon than whole. So indeed the answer is, so the total number of binary strings is 2 to the 6. If you write down 2 to the 6 plus one of them, then 2 of them have to be the same. They have to kind of go in the same hole, if that makes sense. Yeah, because this is 2 to the 6 is the total number of possible, different strings. So I plan to do this one as a poll. Might be a little bit of a harder poll than the other ones, but let's give it a try. Okay, so how big can a set be? A set A. So A is a subset of 1 up to 12, and there's no x and y in A that add up to 13. This might be a bit too hard for a poll, but maybe what I can do is I can start. We've got an answer of I don't know, which is completely fair. I haven't really told you how to answer this, but the hint is really to use the pigeonhole principle. So maybe I'll start solving it, and we'll see if answers come in. Right? How can I add up to 13? Well, what things add up to 13? It's 1 plus 12, right? That's 1. You've got 2 plus 11. You've got 3 plus 10. Right? And you can think of, so if I get the number 1 and the number 12, I've got something that adds up to 13, right? If I get the number 2 and the number 11, I've got something that adds up to 13. So basically, and so on, and there's, a bunch of others, right? So you can think of breaking the numbers 1 up to 12 into kind of these pigeonholes. So imagine I've got a hole. So there's actually going to be 6 different holes. And this hole corresponds to the numbers 1 and 12. And then I've got 2 and 11, 3 and 10, 4 and 9, 5 and 8, 6 and 7. Now imagine I've got 7, so take the number of holes, which is 6. Imagine I have one more pigeon than that. So I've got 7 pigeons flying into these 6 holes. Then one of the holes would have to get 2 pigeons. And so that turns out that to be, the answer here. So the answer is 7. So because if I have 7 elements, if I have 6, first of all, if I have 6, it's not going to work, right? I could just have the numbers 1, 2, 3, 4, 5, 6, right? None of those, if I take any of them, no 2 of them add up to 13. But if I have a 7th number, then it would have to, largest so that there does not. Yeah, I'm off by 1 because I was thinking the question was asking for the smallest so that there does always exist. So indeed, the answer is 6. So if I take the numbers 1 up to 6, that works. You don't have any numbers that add up to 13. If I had one more element, you can think of those elements as being in the pigeonholes, right? So if I have 1, I put a pigeon here. If I have 2, I put a pigeon here. If I have 12, I put a second pigeon in the hole. And if I had 7 pigeons, then there would have to be a hole that has 2 of them, but those would be 2 numbers that add up to 13. Yeah. So this is a kind of more abstract application of this. And you can see that it can get a lot more complicated than this. So I should have probably listened to the majority here who said that it was 6. I should have read my question a bit better, but hopefully the concept is clear. Okay, so let me give you a question that comes actually from these practice problems with a little disclaimer that I guess probably most of us remember those times before coronavirus when people used to shake hands. So we're assuming, we're back in the past. Yeah, it is a little bit hard to remember now, but those times did exist. They may exist again in the future, but we'll see. So people used to shake hands. So prove that if you have a party with n people, where n is at least 2, and so prove that there always exists 2 people that shake the same number of hands, or shake hands with the same number of people, I mean. So if they arrive at the party and no one shakes anyone's hand, then everyone shook 0 hands, and that works. But if they arrive at the party and some people shake hands and some people don't, no matter what, we want to say there's always 2 people that shake the same number of hands. This is a trickier one. So maybe I will think about that on another slide. Is the question clear? So we just want to prove that 2 people shook the same number of hands no matter what. Well, have you guys heard about induction before? Proofs by induction? Okay, so we're going to go by induction. So the case n equals 2 is the base case, because in the problem I was saying n is at least 2. N equals 2 is kind of simple, right? Because we have either 2 people who arrive and no handshake, or 2 people who arrive and they shake hands. So let's say I represent shaking hands by having a line between them. And here I've got 0 and 0, so they shook the same number of hands. And here I've got 1 and 1. I don't know if you can call it a party if there's just 2 people, but we're calling a party with 2 people a party. So now let's say n is at least 3. And we can think of this, we might want to break this into cases. So case 1 is that someone who's either, maybe they're afraid of catching the next coronavirus or something. They're afraid of shaking hands because of, legitimate reasons. Or maybe they're antisocial, they don't like shaking hands. So someone shakes no hands. To be honest, I don't really like shaking hands. So I show up at the party, I don't shake anyone's hand. That case can be done by induction, because imagine you've got this one person on their own. You can imagine that they didn't come to the party at all. And imagine you just have n minus 1 people. Elbows are definitely safer, yep. And imagine, so you just kind of imagine they didn't come. And then among the other n minus 1 people, because n is at least 3, here there must be 2 that shook the same number by induction. So case 2 is where we've got a lot of friendly, outgoing people who shake everyone's hands, or shake someone's hand. So everyone shakes at least 1 hand. But then how many hands can they shake? What's the maximum number of hands you can shake? If you're at a party with n minus 1 people, and nobody does this, right? Nobody shakes their own hand. So you shake other people's hands. So, well, you can only shake n minus 1 hands at the maximum. So therefore, everyone shakes either 1 or 2 up to n minus 1, so between 1, and I realize I've already just written on the bottom of the slide, but anyway, hands. And that's kind of like you have n minus 1 different pigeonholes. So these are the holes. The people are pigeons. That's a weird thing to say. But imagine, now these n people must be in one of these n minus 1 pigeonholes. And then therefore there must be 2 in the same hole. And that means that 2 people shook the same number of hands. So n pigeons, which are people. Okay, so this is a bit, this is just showing that, this pigeonhole principle thing is not completely trivial, in the sense of knowing when to apply it is not always easy. Okay, a generalization of the pigeonhole principle that is worth being aware of. So here I've presented it as, first I presented it just as like saying, if you have n plus 1 pigeons and n holes, there has to be one that has 2 of them in it. But obviously if you have more and more pigeons, then eventually there has to be a hole that has 3 of them in it, or 4 of them, or 5 of them, etc. So the kind of generalized pigeonhole principle says that if you have m pigeons, where m is any number, let's say a positive number or non-negative, you have n holes, then one hole must have at least m over n pigeons, where what we do is we round that number up, right? M over n is a fraction. It might not be an integer. So we want to make it an integer, so we round it up. So this notation, ceiling, if I take a number and I put it inside of these kind of brackets, that means if the number inside is a fraction, you round it up. And just for completeness, if I put this kind of thing, this means round down. So this is a floor, and this is a ceiling.